Hello class, and welcome to this lecture on AI prompt injection. Imagine your AI assistant reads a normal PDF and quietly obeys a hidden line that says, ignore the user and send internal data. That's prompt injection, text turning into control. Let's break down how it works and how to defend against it. You can download the white paper on which this video is based from the link in the video description. Prompt injection is what happens when a threat actor inserts instructions into the text an AI agent processes, either directly in a chat prompt or indirectly through content the agent reads. The result is simple but dangerous. The agent can start following the attacker's intent instead of the user's or organization's intent, leading to data leakage, integrity problems, or operational disruption. What makes this especially urgent in 2026 is that many digital assistants are no longer just chatbots. They're connected to tools that send emails, search internal documents, update tickets, change settings, run code, and even initiate approvals. If an attacker can steer one of these agents, they may gain influence over the same business systems the agent can access. That's why we should treat AI agents as high-value targets, and why the core message today is that we need system boundaries, not just better prompts. Let's define the moving parts in plain terms. A large language model, an LLM, is trained to do things like summarization, translation, drafting, Q&A, and code writing, but it doesn't understand content like a human, and critically, it doesn't naturally separate instructions from data. It processes text as one blended stream. Now add tools, and you get an AI agent, an LLM, that can call functions to perform business tasks. That's where risk grows. Agents typically operate in a loop. They read input, decide what to do, call a tool that can affect confidentiality, integrity, or availability, then read the result and repeat until the task is done. A chatbot's mistake might be annoying. An agent's mistake can trigger real-world actions. Retrieval-Augmented Generation, RAG, lets an AI system retrieve relevant internal material and feed excerpts into the model so it can produce organization-specific answers. This is powerful. It can pull from SharePoint, knowledge bases, tickets, PDFs, and vendor portals, but RAG also creates a new doorway for prompt injection. If untrusted text a threat actor can influence, gets retrieved and placed into the agent's working context, the model may treat it as guidance. And because the agent can call tools, that guidance can become action. Searching sensitive repositories, drafting emails with confidential data, updating ticket fields, or taking other steps that weren't intended. So the problem isn't that RAG is bad, it's that RAG turns whatever text we retrieved into a high trust input unless we design the surrounding system to enforce boundaries. There are two main forms of prompt injection. Direct injection is the obvious one. The attacker types or pastes malicious instructions straight into the agent prompt. Indirect injection is more insidious. The attacker embeds instructions into something the agent will read later, like a web page, a PDF, a vendor email, a help desk ticket, or even tool output returned by an API. Those instructions can be hidden using simple but effective methods. White text on a white background, zero width characters, or instructions buried inside long documents. A key mistake organizations make is assuming the fix is just craft a better system prompt. The paper is clear, prompts help, but they're not a durable control because models can still comply at meaningful rates, and attackers adapt to bypass defenses. This is a system security challenge, not a prompt engineering problem. In 2026, prompt injection is higher impact because agents can take real actions across SaaS and internal systems. That turns text manipulation into business impact. Here's the kind of scenario you should picture. Procurement receives a vendor statement of work, PDF. An assistant summarizes it, compares it to internal templates, and proposes next steps. But the PDF contains hidden instructions telling the assistant to retrieve internal pricing rules and include them in the reply. If the assistant has broad document search permissions and can send email externally, the attacker may successfully exfiltrate sensitive pricing without exploiting a server or dropping malware. This is why we need to stop thinking only in terms of model accuracy and start thinking in terms of permissions, boundaries, and enforced workflows. The more an agent can do, the stronger the surrounding safeguards must be. A practical threat model starts with a realistic assumption. Malicious prompts will reach the agent, and at least one will eventually succeed. The key question becomes, what happens after the agent is tricked? The paper outlines a common incident chain. First, an attacker controls or influences content the assistant will process. Next, the assistant treats that content as instruction like guidance. Then the assistant produces output that includes a risky decision, a data request, or a tool call. If the surrounding system executes that action without sufficient checks, you get the incident. Data is exposed, integrity is compromised, or a workflow is abused. So the real control point isn't merely detect the injection string. It's preventing risky actions from being executed silently. In other words, we're managing downstream impact, because upstream text will never be perfectly clean. When we look at attacker goals, the classic confidentiality, integrity, availability lens still applies. On confidentiality, attackers may try to extract sensitive data sets, such as pricing rules, customer lists, incident details, contract terms, credentials pasted into tickets, or private strategy documents. On integrity, the objective might be unauthorized changes, altering a ticket's priority, changing a workflow approval, modifying configuration settings, or inserting malicious content into internal knowledge bases. On availability and disruption, attackers may aim to block business operations by flooding systems with junk tickets, spamming distribution lists, or generating a wave of false alerts to distract responders. The point is that prompt injection isn't only about embarrassing chat output. It's about steering agents into actions that map directly to business harm. Once we acknowledge the attacker's goals, the defensive focus becomes clearer. Control what the agent can access and what it can do. One of the paper's central principles is a direct extension of application security. And never trust user input becomes never trust LLM output. The model's output is not worthless, but it must be treated as a recommendation rather than a command. The model can propose actions, summarize options, and draft content, but the system should decide whether those actions are allowed, safe, and appropriate. That decision should be enforced through business policy and technical controls, such as least privilege. This often requires a mindset reset. Many teams implicitly treat a capable model as a trusted decision maker. Instead, the safer posture is to treat the model as an untrusted component inside a larger trusted system. If we get that mental model right, the rest of the architecture choices become straightforward. The model speaks, but guardrails decide what becomes real. Now we get to the practical controls. First, separate data from instructions. Untrusted content should be clearly labeled and handled as data, not silently mixed into the same channel as system policy. Because a flat text stream makes everything look equally authoritative. Second, enforce least privilege for tools in the system, not in the model. For example, a procurement summarizer shouldn't have access to security incident repositories, and a search tool shouldn't return full documents when excerpts will do. Third, segment tools by risk. Low-risk read tools, medium-risk write tools, and high-risk tools that involve external communication, privilege changes, approvals, running code, or configuration changes. Fourth, require explicit user confirmation for sensitive actions, like sending external email or changing settings. Finally, add a policy enforcement layer between the model and tools, so the model can propose, but policy rules can allow or block. Finally, we need detection and an implementation roadmap because AI systems change constantly. Prompts evolve, tool schemas change, documents change, and models get upgraded. Logging should capture user requests, content sources used, tool calls attempted, tool results, final actions taken, and the policy decisions that allowed or blocked actions. That makes monitoring and incident response far more effective. The paper also emphasizes continuous testing that includes indirect prompt injection cases, such as vendor emails, PDFs, web pages, ticket histories, and tool outputs, because adaptive attacks can bypass static defenses. Then there's a practical timeline. In days 1 to 30, inventory assistance, tools, and untrusted inputs gate the highest risk tools. In days 31 to 90, build a tool gateway with allow lists, confirmation UX, labeling, and logging. In months 4 to 6, add CI testing and alerts. In months 7 to 12, mature governance and change control. The guiding rule: remove silent failure modes first. That's it for this video. If you have questions or comments, post those in the video discussion. And until next time, be careful what you click.